So let's look at the first one. Which of the following problems can be solved by algorithm with linear running time? Well, n is the length of the list. So the correct answer is the second and the third. Okay, I think you should know how to solve these two problems in linear time. Okay, the first question, right? So it's worth mentioning that in class we have solved this problem with the algorithm that's quadratic. Okay, but it's also possible to leverage a sorting algorithm to sort the list first, and then with a single for loop, you can check for duplicates. So such kind of algorithms running time would be n log n if you use merge sort or quick sort or heap sort for the sorting. Okay, but still is not a linear time algorithm. Okay, so move on to the next question. The worst case performance of quicksort is theta of n squared. So this is true. So here's why. All right, so remember quicksort works by first partition array into two parts, right, or three parts. The first part is composed of elements that are smaller than or equal to p, and we have a pivot value, and then the second part is elements whose value are greater than p. So in the worst case scenario, the pivot value that you pick, right, could be the smallest element or the largest element, but no matter what, the recursive algorithm function will look like this, right? So you spend linear time to partition the array, but then you end up with very unbalanced partition, right? So one contain no elements, the other one contain everything except the pivot value. So if in every recursive course you end up in this kind of a scenario, so you have overall this recursive algorithm characterizing the running time. So you can solve this to get the worst case performance to be quadratic. All right, so that's a second question. So third question, computing the median of an array is easier than sorting that array. So this one, it is true, okay? The reason is the following. Okay, so first of all, we do have a linear time algorithm to find the median of array, which unfortunately we didn't talk about, right? On the other hand, right, sorting arrays, we know, yes, it can be done in linear time if we use counting sort and radix sorting algorithm. But in general case, right, when we don't know the type of data that's stored in the array, so this kind of sorting algorithm usually do not work. So we can assume we need to use comparison-based algorithm for sort array. So in this case, the second kind of problem require n log n, right? So that's running time, and computing the median, the complexity is n. So therefore, this statement, it is true, but I probably will not text this one, given that we didn't really look at the selection problem. Okay, so problem number D. For any algorithm, if it is implemented as a recursive function, then it is divide and conquer algorithm. So this is a false statement, right? So I can give you a counter example, right? So bubble sort algorithm can be implemented as a recursive function, but it definitely is not a divide and conquer algorithm. So the answer is false. Problem number E, which of the following sorting algorithms are not based upon comparison? So counting sort, right? So this is a solution. I would not spend too much time. Repeat. F, compare two pairs of, one pair of a rounding function. So the first part, all right, so let's just compare them first, use the mathematical rule we learned, okay? So let me cross this out. So let's simplify the left hand and right hand, okay? And then let's talk about the rounding term. So the left hand side, okay, maybe just say log base 2 to the n of 3, but it's actually equal to 3 times log base 2n. Okay, so, and the function we have here, log 2 to m, is actually equal to log 2 plus log 2n. All right, so, and this one is 1. So now if you look at these two functions, you will realize that actually these two functions have the exact same growth rate, because constant coefficient does not matter, lower order does not matter. So that means the first part of the statement is true, but the second statement is false. So indeed, the first function is big O of the second function, and in the end, they are actually big theta of each other. So this is a false statement. Okay, number G. We have two functions here, and we want to see which of the statements are true. So notice that they are so-called polynomial function of n, right? In that case, remember the rule is that, right, look at the exponent, right? So 1.2 is larger than 1.1. That means g of n dominate f of n. Okay, so whenever you have this, right, the following is true, right? F of n grow no faster than g of n, and on the other hand, we don't have the rest going. Okay, so g of n grow is f of n, which is equivalent to say f of n is big O g of n, but not the reverse. Or the converse is not true, so only this one is true. H. So here we are comparing two exponential function of n. All right. So similarly, right? So we have seen that the base matters. So g of n is dominate f of n, right? So g of n grow faster than f of n. Okay, so right, we also know what it means mathematically, right? So this means it go to 0 when n go to infinity. Okay, so translate into big O notation, right? F of n grow no faster than g of n, so that what big O stands for, right? Please remember a way to make them to remember them big O, big omega, big theta is that you can kind of think big O as less than equal to relation. Okay, you can kind of think this as fn is greater than or equal to g of n. And the third one is kind of saying their growth rate is the same. So hopefully that will help you remember the meaning of the three notation. Okay, moving on to the next page. Explain what situation it makes sense, under what situation it makes sense to use counting sort algorithm to sort a list of elements. So the answer is, right, one, the list contain let me just restart. Okay. Done it. Okay. How do I do that again? Okay. So the answer should be one, the key, right? Type is of integer type, and take values from finite. I mean, in other words, relatively small range. Right. So, for example, right, all the keys might be in the range from 0 up to k, right? Well, k is much smaller than the list length, which is n. So otherwise, it's not worthwhile, right? So remember, we are using some kind of array. We usually call it count C, right? Which is used to count the number of elements that take value 0, take value 1, and all the way to k. Okay, so this is to keep track, right? To count the number of times that we have seen a key of value I, right? So for example, if it's in general, right, this value says 5, this will means I have 5 elements with key value 5. Okay, so moving on, right? Demonstrate how radix sorting algorithms sort the following number into ascending order. So I'll skip this one as we have looked at such problem in class. So the second big question, analyzing running time of algorithms, okay, and express them in bigger notation. First question, okay, so we have a function, okay, and you can see immediately that is a recursive function, okay. Whenever you have a recursive function, you will know that you will be writing a recursive algorithm for the running time. So I highly recommend you define the function, right? So make it clear that let T sub m represent the number of steps which it takes this function to calculate to compute. Okay, so total number of steps it takes for factorial n to return its result. Okay, so now we are going to analyze or write a formula for T sub n based entirely on this code. So we all know that these are the two base cases, and this is a general case. Okay, so for the base case, right, we're going to write the t sub n separately, right? So for t n equal to 0, we just return 1. That means when n is 0, when the input to this function is 0, so we just have one step and then we're done, right? So the total number of step is 1. Okay, so similarly, when n is 1, okay, when the input parameter is 1, so we're going to have one step, two step, right? Totally 2 step is enough. Okay, but otherwise, that means when n is greater than 1, okay, so we'll be at the general case. Okay, so what happens here is, okay, so we will execute this statement, which will for which we first need to call this function, right? So this function will need some step to finish the work. So, but how many steps it requires for factorial n minus 1 to finish? Now is the time to remember t sub n's definition, right? So t sub n represents the number of steps it takes factorial n to calculate. Now we have factorial with parameter n minus 1. So the number of steps here should be t sub n minus 1, okay? And once this function finish, we need to multiply its return value with n. So that's another step. And then we return. So that's another step. So add 2 to it. Okay, so this is recursive formula for t sub n. So we need to solve this. So obviously, master theorem does not apply here. So we need to use the massive iteration to solve this. Okay, right. So we already have t sub 1, t sub 0 is 1, t sub 1 is 2. Now how about t sub 2? Okay, t sub 2, we have to use this formula to relate it to t sub 1 plus 2. So that means 2 plus 2. So let's do a few more steps. Right, t sub 3 is t sub 2 plus 2. Okay, so t sub 2 is here, copied it down, plus 2. So that means maybe it's 3 times 2, right? Tentatively, I can write this down. So let's do one more until we are clear about the pattern. All right, t sub 3, all right. So 3 plus 2, 3 times 2 plus 2. So that is 4 times 2. So it seems pretty clear now, right? So you can guess, okay, t sub n seems to be 2n. Okay, so, and which is big theta of n. Okay, so basically we're dropping the constant coefficient to get the simplified expression for the rounding time. Right, so getting to the next problem. So here we are faced with a function, okay? Take an integer as input, which is a positive, and inside of that, we don't have a recursive call. Instead, we have a nested for loop. Okay, so here I'm going to explain to you again how to handle nested for loop. Okay, so in the review sheet, I explained to you, but here is an example, right? So what we need to do is we need to unpack the nested for loop, right? So for each iteration of the outer for loop, right? So I will start from iteration. Okay, for each one of them. So that means we know I need to start from 1 and then go to 2 and go to 3, and all the way to I equal to n squared minus 1, and I equal to n squared, right? So this is easy. Just look at the outer for loops header. You know the range of value I need to iterate through. Okay, so now for each of this iteration, right, let's look at the inner loop, right, and how many times they will iterate. So the inner loop, right, says that the j will start from 1 to 3. Thankfully, right, so this will always be 3 times, right, iterate for 3 times. So that means the innermost statement, which I circle here, will repeat 3 times here, 3 times here, and every place. Okay, so this is due to the fact that the inner loop's header, right, does not have any dependency on I. It's always j from 1 to 3. So that means every single outer loop iteration we have 3 times here. So overall, right, total iteration, total time, number of times the statement in the very innermost loop is repeated is just 3 times total number of iteration here, which is n squared. So overall, right, so the running time, which is total number of steps for this function, is 1 here, 1 here, that's 2, and then 3 n squared. Okay, so we drop the constant coefficients, drop the lower order term, we get this simplified asymptotic running time. Okay, so let me take a pause here. So I will resume later to continue with the rest of the question.